value is the output entropy. So it should be Ri. That's called Ri plus 1. Conditional on the input. A conditional no input. So conditional on this. I believe it should be Ri. All right. Okay. Hopefully it's correct. Okay. So it turns out what happens is that if you look at all these values, okay. It's getting late. Let's see. If you sum up all these entropy, my student claimed the following.
That is a cop-out.
That's a cop-out, huh? What's his thesis? Xi R. Yeah, it should be all of them should be removed in a complement. Okay? So this is precisely the entropy of R, some set R tilde M conditional on the input at Rm. Oh, it should be. Yeah, it's fine, right? Yeah, I think the notation is a bit sucks because I should call this both complement, really. So let's see, maybe I should call this YR plus 1 complement. Yeah, so maybe this is a mistake. Don't ever grab slides from your students and not check it carefully. This is R1. This is R1 complement. Yeah, these are all complements on the downstairs. And that will match up with my omega complement here. And then the output should be YRI plus 1 complement, conditional on XRI complement. And everything should be complement. All the sets should be complement. And this inequality basically tells you that the sum of the cut values, so the point is that these sets are now varying with time, whereas you want to relate it to cuts which have invariant sets, in other words. Okay, so it turns out that you can show that the sum of these entropy, it must be lower bounded by the sum of entropy of these invariant cuts, where the set Rm tilde is the set of all nodes that appears at least m times in Rj. All right. So there's some kind of averaging argument here, basically, to show that essentially the sum of this cut value, it must be low bounded by the average of a bunch of horizontal cut values. Okay. And this proof is based on some modularity of the entropy function. Please don't ask me how to prove it now. Thank you. Sorry? Okay. All right. On that note, no, you can prove that using Raymond-Young's program. So you can plug this in. If you don't believe me, you can go on your computer right now and plug this into Raymond-Young's program. It will say yes. Yes, we can. Yes. Yes. Okay. All right, it's getting late. So, okay. So we have now a result for the deterministic network. And now we can bring it back to the Gaussian network. And I'll be a bit brief here, because otherwise the notation gets really messy. And remember what we're doing in the deterministic case. The source encodes the message over t symbol time for equal length network, over many symbol times for arbitrary network. Each relay randomly maps the received signal into a transmit code word, random coding strategy. D collects all the information received from a relay and decodes the message. Okay? I don't know why we use the word deterministically, because of course it decodes the message deterministically. Anyway, this strategy is optimal, okay, in the deterministic case. So in the Gaussian case, we can try to mimic the strategy. So here's a mimic. the source encodes the message over T symbol times. Okay. Each relay, now each relay, in this case, receives something which is essentially the bits that are received at above noise level. Right? Because in our model, in a deterministic model, we are essentially only looking at the signals you receive at the noise level. So what I'm going to do is to try and mimic this by having each relay essentially try to get those bits out from the received signal. And it does that by quantizing the received signal at the noise level. So to do this mapping, okay, you basically have to convert your problem into a discrete problem. And to do that, you basically quantize the received signal at the noise level to essentially get the bits above noise level in the deterministic channel. Once you do that, you can now randomly map it into a Gaussian code word. Okay? And now, decode the message. Now it's not so simple as in just checking a table to find a unique map, but it needs to decode by finding a message which is jointly typical with the received signal. Okay? Now, essentially, what's happening here is that, okay, this is a very simple strategy. So there was a question earlier on how much information do you need to implement this kind of strategy? If you think about what's happening here, essentially, each node is doing two things. One, it is quantizing the received signal at noise level, something it can do locally. Two, it is mapped to a random transmitted code word, also locally. So therefore, relays actually do not need to know any channel information, any global channel information, or even the channel going forward. Okay? How does this perform? So it turns out that we can analyze this problem pretty similar to how we analyze the deterministic problem, except that essentially you have to put some fuzz around the problem. So before, the message M, when you encode it, is mapped to a deterministic vector to output. Now, because there is noise in the problem, you have to sort of put a fuzz around the message and a ball. Okay? And as you propagate that network, okay, the ball will get a bit bigger. However, the size of this ball is roughly given by the noise variance. And so what you need to show is that when you have two separate messages, what's the probability that your received vector lies in the intersection between two jointly typical balls? The analysis there is somewhat similar to the analysis for the deterministic channel, but with much more work to essentially deal with the delta and epsilon to make sure that the performance loss you get by having this fuzz is not that big. And so finally, we proved a result, which is the following. Okay? For any Gaussian relay network, okay, the capacity of the relay network, which is unknown, is upper bounded by the cut-step bound. This is, of course, not our result. This is theorem 14.10.1. But using our scheme, we can show that we can achieve to within a constant gap from the cut-step bound. And this constant is independent of the channel gains or SNRs of the link, so universal constant. However, this constant at this moment, unfortunately, depends on the size of the network in terms of number of nodes. So our best bound so far is the constant is 5 times the size of the network. Now, this is not the most practical result at this point because this gap is still large. And in fact, we're not very happy with the fact that it depends on the global property of the network. We're hoping to get some constant gap which is independent, depends only on local property of the network, like the n degree or something like that. So we're still working on that. But at this moment, that's the best result we have, which is the gap. We do have a guarantee, and the guarantee is in terms of parameter which does not depend on channel gain, but depends on the number of nodes. Okay? Yeah?
You mentioned that there is a quantization. Does that mean something like a compressed forward?
So that's the whole point of example number 3, the third example. So here we're not doing compress and forward, at least not the Gaussian compress and forward. What we're doing is we are always quantizing at noise level, Okay. And then we're forwarding the we map that to a random code word. So in other words, the destination does not try to actually decode the received signal at a particular node. It only cares about decoding the final message based on everything it collects. Okay? So right now, we still have not shown that our strategy is not subsumed by compress and forward, because compress and forward has this auxiliary random variable which we don't know how to deal with. But I think we're pretty convinced that example that Gaussian compress and forward will not be able to get this constant gap bound. So our strategy is better than that. Whether you can get by with other input, we don't know. Yeah?
I was wondering how practical your scheme could be, because to me it seems like using the achievability tool for channel coding, for doing the real channel coding, so don't do the random coding for the real channel codes. You see?
Sorry, I don't understand.
The random coding scheme that you have seems to be not computable, because the receiver should know all the mappings and computing. I mean, from implementation point of view, it's just for the existence. It's okay.
Yeah.
You have all the grounds on your
Right.
But from implementation point of view, it seems that you cannot really.
Yeah, so the next step to make it more implementable will be essentially follow the lines of network coding, right? To first see if we can get by with some simple linear encoding schemes. Okay? And actually, if you think about it, even network coding, we bring back to yesterday, has this related issue. Is that if you use random network coding, which is now sort of one common approach to go, then you can ask, hey, maybe the decoder also needs to know the random mapping. And that's also a problem. So one way of resolving that, as far as I understand from the network coding field, is one, you can embed on your header or your packet the equations that you're using. Two, even if you don't have that information, you can try to do some non-coherent decoding. So that's the Frank Shishang approach and Ralph Carter approach, non-coherent decoding. So maybe some of those ideas. I do not claim right now that this result is practical. But, however, as far as I know, this is the first result, which gives a high guarantee on performance on an arbitrary network. But
about choosing the code word, you said that there exists some random code word. You didn't say that with high probability the code word works.
Yeah, but the standard
code word should be strict. But for random network coding, any random code that you pick with high probability will work. But for this scheme, you have to find that code word.
Why? But it's similar, no? The random coding argument says that on the average it works well, and then you can use some kind of bounding argument to show that with high probability it works well. And I believe similar, I didn't do the detailed calculation, but I believe similar ideas can be used here.
It's the same proof idea.
Yeah, actually the funny thing is that if you think about the root of this kind of proof technique, it's essentially in Slepian and Wolf, I believe. Slepian and Wolf, when they proved the multiple access channel achievability, they look at a bunch of pairwise error events, which corresponds to events where one user is wrong and the other user is right and so forth. Essentially, those corresponds to the cut in the multiple access channel. So essentially, Raymond Young, probably not knowing, is reinventing that kind of proof style. Yeah. Yeah.
Kind of difficult to believe this 5 times the size of the network to be the gap between the upper bound and the achievable, because we can always put as many copies of the network to get your seed to get as much as you want to get larger and larger. But the 5 times size of the network is always constant. And then you can get rid of that by making the copies of your network. See what I mean?
I didn't quite understand this copy of the network
I'm
business.
saying that you can always increase the seed by like putting as many copies of network as you want on each other to increase the capacity of each link by big factor.
Okay.
But this 5 times V is always constant.
like having higher SNR.
Yes.
Yeah, high SNR.
So you're increasing your capacity, but that size.
Yeah, that's the point. But that's the point of this kind of result, right? The point of this result is that as SNR goes to infinity, this gap is fixed independent of the SNR.
If you look at this result asymptotically, I mean, then it seems that this is the right, the exact capacity, because you can always assume that you are, instead of using your network in like, instead of extending your network in the space, in time dimension, you can always extend it in the space dimension. I mean, we can have parallel network working together to...
Having parallel,
I mean,
equal to having a huge maybe higher SNR.
No, I think you're talking about, this is my interpretation of what you're both talking about, so I could be wrong. But I think Sadek is talking about using the network twice, or twice as often in time, and that won't increase the kappa. But my guess is the kappa will also get multiplied by 2 that way too. I'm not sure because you're bringing in time.
I think that's like adding nodes, right? No?
No. Just putting parallel edges for your network, like instead of using in.
Like the Gaussian channel, okay.
I mean, that is number of nodes.
So this is bits per second per hertz, yeah? This gap is in terms of bits per second per hertz.
Okay.
So when you're adding parallel link, you're effectively increasing the bandwidth, right? So this is bits per second per hertz, normalized already by the bandwidth.
I think it will scale.
They're normalized by.
Yeah, all the results that I talk about today is all in terms of bits per second per hertz.
It's not a constant, yeah. I mean, so you're saying that the capacity is already normalized by something.
Yeah, the capacity is always bits per second per hertz. Always bits per second per hertz. Let me just take a few questions and maybe we can have a discussion afterwards. Yeah?
So could you explain a little bit more how do you do the quantization?
So you receive, okay. So the question is how do we do the quantization? Okay? So okay, so at each node you receive a signal y, okay? Right? And this y is a real signal. Okay? And according to the deterministic strategy, I'm not really interested in the part of this. So you can think of this signal as again some binary expansion, right? Okay? Right? Or what I'm interested in to mimic my deterministic strategy is to try to figure out these bits on the left of the decimal point. Okay? So I try to mimic that. And the way I mimic that is I want to quantize it at the noise level. Noise level really means this decimal point. So now I'm quantizing things at this with this error. And this will give me a bit representation of y. And roughly speaking, not exactly, it will be these bits. Okay?
So scalar quantization and
Vector quantization. Actually, to prove our result, we need vector quantization. Yeah.
so in general you said that it's not equivalent to compress and forward. So maybe try comparing this exact speed and basically this is a near achievable result. So you compare the result for this boundary layer network transform to decode and
Yeah. So we have some problem in doing that. And the problem is because in compressed and forward, there's an auxiliary random variable, right? Which is how you do quantization. Remember, for example, if you do y is if, there's a random variable u that you map your signal into, right? Now, for y is if, u is for the Gaussian source, the u is Gaussian. Yeah. But for this problem, it is not clear. If you set, because your goal is to, if you set it up, it's not clear whether the optimal auxiliary random variable, Gerhard can correct me if I'm wrong since he's an expert in this, whether that random variable can be guaranteed to be Gaussian.
It's almost certainly not.
Yeah, almost certainly not. So therefore, it's essentially not very computable, right? Because if I don't know it's Gaussian, then I don't know how to compute it.
But maybe I think just as a comment to this, I mean, if you do, the usual way compressing forward is stated is that the destination you do a two-step decoding. You first decode the signal from the relay, and then you use that to get your quantization output, and so it's 3 steps, and then finally you decode based on the 2 outputs, the quantized one, the other one. But if you did a full joint decoding of both, of everything all at once, rather than going through 3 steps, then I think, I mean, it depends what you call compress and forward, I think. Do you require this decoding to be done in a, I don't know, step-by-step way or not, at least for the relay channel? For the other case, it's different, because you don't do any decoding at all at intermediate stages, right?
For our scheme?
Yeah, you don't do any intermediate.
No decoding.
You decode right at the very end.
Oh, right at the very end,
So
right.
that is unique. But I think for the relay channel, you can make it, you can kind of put them together into one scheme. You can call it compress and forward. You can do a joint decoding of the message that you transmitted rather than doing it step-by-step.
That's one issue. But another issue is the choice of the auxiliary random variable, though.
Yes, so that has to be optimized in some way. But you have that too in some ways.
No, there's no auxiliary random variable here.
Yeah, you choose it in a very specific way, I think.
Yeah, I choose a very specific way. That's right.
Okay,
So it's a recipe. In other words,
Right.
one can actually compute performance.
Right, so choose it in that way for compress and forward, for the existing compress and forward scheme. If I make exactly that choice for the Gaussian channel, I think the question was, is your rate going to be better than compress and forward? But my guess is it's actually, it's a special case of compress and forward if you do a joint decoding, which I don't think does any better than doing the step-by-step decoding.
Could be.
That's
But-
my guess, it's only a guess.
But how do you define compress and forward when you have multiple stages? For example, look at your paper. It seems to be only one stage.
It's different, yeah. So this is unique in that sense.
I see.
Yeah,
Okay.
so I'm not claiming.
I see. So you're breaking up the problem into 2 aspects. I see.
I'm talking about only a
Got it.
single relation.
Yeah, so we need to think about what auxiliary variable to use in your compress and forward then, or in compress and forward. Whether there's one natural one which maps from this scheme to that scheme.
Yeah, I think this is different. I'm pretty sure.
Yeah.
Also, this bound, finite rate bound, and all the results extend to the multicast case. And
Yeah.
What about the bound? Anything about the bound?
I believe that same bound works for the multicast case, but I gotta think through this a bit more carefully. I don't know if we actually wrote that down in the paper.
Probably is the same, right?
Yeah.
Because the V comes from the longest
Yeah.
path
Doesn't
possible
depend on-
through the network.
Yeah,
because
probably.
The balls are growing, right?
Yeah.
The clouds.
The balls are growing, yeah. So actually one problem of this bound is that the balls are growing. And so we suffer from error propagation, noise propagation problem.
But then there's a lot of it. I mean, sorry, I'm having a discussion here, so you have to stop me.
You're the chair. I thought you're the chair. I have to stop you.
Doesn't it depend on the number of hops you take then, rather than the V, right? Why is the size of the clouds a function of V rather than the number of hops? Are you just upper bounding the number of hops by the number of V?
Yeah, so the problem here, if I remember correctly, is that each of, the problem is that, okay. So there are several steps improving this gap, right? So first, essentially what we're achieving, if you think about the K-step bound, okay, good. Let's go back to the K-step bound. Yeah, so this is the K-step bound. So what we're achieving, connecting the K-step bound, is actually essentially achieving when the input distribution is independent. Because in the deterministic case, what we're achieving is these guys are ID. So what we are also comparing to in the Gaussian case is we're achieving not any arbitrary input distribution, but independent input distribution.
So that C on the right-hand side is for independent.
No. C is for the C bar is optimized over all distribution because that's a valid. Otherwise, it's not a valid K-step bound. However, what we're achieving can be close to the independent input distribution because if you think about our strategy, there was no correlation across the input. So therefore, we need to have a gap between that and the optimal input distribution, and that involves the whole network, and that is where that free comes from. Okay, so Let me finish. Let me finish. All right, so we have this result. So I should give some a little bit of history on this deterministic relay network. Actually, there's a whole, again, actually it's very interesting because if you think about the deterministic approach, actually in the late 70s, I believe, people were very interested in deterministic models. I mentioned the Al-Gamal and Costa paper in 1982 on the deterministic interference channel. But actually, Al-Gamal, with a student, a very famous student, has already looked at semi-deterministic or deterministic relay network. So there's the first paper, single relay, single semi-deterministic channel, classic Al-Gamal, only 1 page long or 1.5 page long. And Gerhardt likes that. I reserve my opinion. I'm sure the Stanford students will now go back to Stanford and say that I'm bad-mouthing Abbas or something. Oh boy, I gotta pay them off like that. Okay, then there was a result, which is Aref's thesis, on relay network with general deterministic broadcast, okay, but no interference. So the important thing about that is that there was no interference, okay? And what we did is, and this work was extended to the multi-cascade with Gerhardt's work and Radecka. I think the deterministic approach was kind of saying, okay, good, let's focus on the deterministic approach because the problem is too difficult. That happened in the early 80s and late 70s. But that's kind of fizzled out. And I think one reason why it fizzled out is because the general deterministic problem is actually quite difficult. Because here, the simplification really comes from interference. If you put interference here, then I don't know if there's any capacity result. Not that I know of. Not that I know of. What we are bringing in the table right now is saying, look, we're interested in more in the Gaussian model because that captures the key aspects of wireless. And this sort of provides a reference to what type of deterministic model is interesting from a practical point of view. And that deterministic model, because of inheriting the linearity of the Gaussian, provides further structure, which allows us to make progress here. So that's how I view the state of affairs and how we come into the picture. Okay, so, all right, so that's it.